Well, hello to everyone, and today I will be discussing two small topics of vibrational frequency and the force constant of enharmonic oscillator, and I will be continuing the same vibrational spectra. And in addition, that the isotope effect on vibrational level. And I hope you will be moving with me itself as I am uploading the daily lectures, very short lectures. So if you'll be going through the daily lectures, then you are be gaining much more and you will be understanding more. So now we have already discussed about this curve. Now the classical vibrational frequency of a harmonic oscillator, we know that nu oscillator is equal to 1 upon 2 pi under k upon mu. This k is a force constant and mu is the my reduced mass of the diatomic molecule. So the separation of successive vibrational levels is constant and equal to this omega is equal to V oscillation divided by C, which is the classical frequency in centimeter inverse, that is in wave number. So in case of the enharmonic oscillator, the classical frequency as given above holds for very small amplitudes only. In fact, it decreases slowly as the amplitude, that is the nu, increases. The exact classical expression for the vibrational frequency of the enharmonic oscillator, the state nu, is given by nu is equal to C of delta Z of nu. So for example, in this curve, enharmonic oscillator curve, then this is the zero level because the 0 point energy. Then you have a first excited state, and suppose we have an arbitrary state, this nu, and above below then this is nu minus 1, above that this level this nu plus of 1. So this nu oscillating, this nu is equal to C of delta of Z of nu. Then here it is simply that delta Z of nu of half plus delta Z of nu of minus half. And just putting this Z of Z nu plus of 1 minus the Z of nu plus of this delta nu minus of, Z nu minus Z nu minus 1. And from here this 1 upon 2 C of Z nu plus 1 minus Z nu minus of 1. One should be expanding it. I know that this is what is the value of this Z of nu plus 1. And simply this in place of this nu, because I know that is this nu plus of half. So in place of nu you need to put this nu plus 1, and this is nu plus 3 by 2 minus this omega e x e nu plus 3 by 2 its square, because this is the enharmonic term, this minus this omega e of nu half minus omega e x e of this term. So once you will be estimating this quantity, and finally you will be getting that this term, very simple algebra it is, then finally this C is equal to omega e minus omega e x e minus 2 omega e x e at nu. So now from this relation, if you look at this frequency, this classical oscillating frequency nu, if nu is increasing, this quantity will be the higher. So the classical vibrational frequency decreases from this relation simply. Now one hypothetical state will be assuming that if nu is equal to half, below that 0 point energy, where this energy is equal to 0, this energy is equal to 0 and vibrational energy is equal to 0, the frequency for this stage is given by, then this is just C of omega e, and this all term rest term are the 0 now. Thus omega e represents the vibrational frequency in centimeter inverse that an enharmonic oscillator would have classically for a very small amplitude, that is at a imaginary state, that is nu is equal to 1 upon 2 minus 1 upon 2 at a very bottom of the potential curve. From the vibrational frequency omega e for infinitesimal amplitude, the force constant Ke. Now we are representing this Ke of the enharmonic oscillator for this infinitesimal displacement may be determined with the help of this V oscillating is equal to C of omega E, and omega E, this V oscillating, we know that 1 upon under root 2 pi this K E divided by mu from equation number, from this equation. Now in place of K, we have this K of E. Then simply, then from here, this K is equal to, from this relation, then you have this relation 4 pi square mu C omega E square. The force constant K is determined by the electronic motion, sorry, this 4 pi mu C square. Then, for example, if you would like to calculate this Ke for the HCl, then for the mu is equal to this one, omega E is equal to this one, and K is equal to this one. This is a somewhat larger than the value of the force constant K is equal to this, obtained from the harmonic oscillator model. So now once you are considering that the HCl atom behaving like a harmonic oscillator, then the force constant is achieved to be this one. However, in the case of this enharmonic oscillator, we'll be getting a somehow this 5 slightly higher value of it. So now this is just a comparison that how we are estimating that the force constant with the help of this imaginary state, and in addition that the quantities, once we are assuming that the harmonic oscillator and the enharmonic oscillator, what is the change in that force constant. Now the next thing is that how to, as we have discussed already, this how this isotope effect influencing the isotopes in a rotational spectra. In the same fashion, we'll be looking at the isotopic effect in the vibrational levels. So isotopic molecules differ only in mass. Obviously, for the vibrational frequencies are different. Assuming harmonic vibrations, the classical vibrating frequency is given by this, the nu oscillating is equal to 1 upon root 2 pi this K upon mu. The force constant K is determined by the electronic motion only and is therefore exactly same for the different isotope molecules, because this K is determined for the electronic motion only. So once it is a constant for the isotopes, then the reduced mass is however different for the different isotopes. Suppose we'll be defining that omega I stands for a heavier isotope. We have this omega I divided by omega is equal to V oscillating I divided by V oscillation is equal to root mu upon mu I is equal to rho. We are defining with the help of this rho. This heavier isotope molecule has the smaller frequency, that is the rho is less than to 1, because once we'll be putting that this omega I is equal to rho of omega, and this rho is less than to 1 because this mu I is heavier to this mu. Then the vibrational term of the two isotope molecule, assuming that the harmonic vibrations. Once we have only the harmonic, then I could write this z of nu is equal to omega nu of half. And the same fashion, the zi nu is equal to omega I of nu plus of half. And in place of this omega I have this rho of omega, this nu plus of 2. Therefore, the isotope shift of a vibration level nu is given by this z of I nu minus z of nu. Now we have the two states. Now this is for the isotope and this is the normal one. So just putting this value, this rho of omega nu plus of half minus omega nu plus of half is equal to simply rho minus 1 omega nu plus of half. Since this rho is less than to 1, then obviously I will be getting that this is a negative quantity. It means that this zi nu will be always less than to this z of nu, because this quantity is appearing this negative, because this rho is less than to 1. Then this quantity is in the right hand side, it is a negative, so it means that this quantity must be higher as compared to this quantity. So the vibrational levels of heavier isotope are lower than the corresponding level of lighter isotope. Now, so far we didn't incorporate that the enharmonicity of the diatomic molecule. Once you are taking it in account, then simply this z of nu is equal to omega I nu plus of half and this one. And for the isotope, simply this, in place of this omega I, you have this rho of omega I, and in place of this one, you have this rho square of omega I simply. Now, so that, now once you have these two isotope, this is normal, this is the isotope, then we have simply these two relations from here. This omega ei isotope is equal to rho of omega e, and this omega ei of xi is equal to rho square of omega e xe. So the isotopic shift of a vibrational level is now simply again will be defined as the zi of nu minus z of e. Nu, this rho omega e this minus of these quantities. Now the final term will be the positive one. So simply once you will be just a simple algebra again, once you are computing this one, then finally you have this rho minus 1 omega e this nu plus of half minus rho square, this rho square minus 1 this omega e x e nu plus of half its square, this term. Again this minus has been taken outside, then this is the minus term. So if rho is only slightly different from 1, so what we are assuming that if the rho is very slightly different from the 1, then we could put that this rho plus 1 is approximately equal to 2, because this rho is approximately, we are assuming that is the 1, then this rho plus of 1 is equal to 2. Just factoring this rho square minus 1 is equal to rho plus 1 and rho minus 1, and taking this term outside, this rho minus 1 taking outside, this omega e and nu plus of half minus, because this rho plus 1 is equal to 2, then this is 2 of omega e re nu plus of half its square, and this term. So finally you will be getting that this rho minus 1 outside and nu plus of half itself, and rho omega e minus 2 omega e x is nu of half its square. Since this rho is less than to 1, this rho is less than to 1, the z of I isotope of nu minus e is a negative quantity. Again from here itself it is a negative. So even that we are taking that the anharmonicity in the picture, then still that the vibrational levels of the heavier isotope are the lower than these of the lighter, and the shift between the corresponding levels increases with increasing the nu, because this nu is increasing, the shift is increasing. So if you look at in this energy diagram, so means that we are increasing, if we are going for the higher level, that is the shift is increasing, means that this will be changing rapidly, means once we are going for the higher level, then their isotope effect is significant. What the same thing we have achieved in the term or in the case of our rotational spectra as well. The shifting in levels results in the doubling of the vibrational bands. Once both the molecules are there, so you have a doubling of the band. The bandwidth will be just of the double. So corresponding to 1, you have a one band, one fundamental band. Corresponding to its isotope, there will be the fundamental band again, or for any excited band itself, but they will be almost overlapping to each other. So the band shift now, once we will calculate what is the band, this delta nu is equal to this delta I minus of nu, because these two bands are overlapping, and from here this nu I we can simply calculate this zi from the zi to the transitions taking place, the zi prime to the zi double prime minus the zi prime minus g prime minus the g of double prime, then putting these prime terms together and the single prime together, then we know that this quantity, what exactly this quantity, that is the rho minus 1, this omega nu prime plus of half, and this one is rho double prime of half. Then from here finally this rho minus 1 you are taking out, omega nu minus of nu double prime. Thus for the fundamental band, this nu prime is equal to 1 and nu double prime is equal to 0. So what we obtain, that is delta nu is equal to rho minus of omega. So the shift increases as the order of the band value of nu prime is increases. Suppose means once I am increasing this nu, the value of this we are increasing, so the band value will be increasing in the infrared spectrum of a, for example, in the infrared spectrum of SCL, each band is in fact a double band, one corresponding to HCl35 and the other one is HCl37. In the very first, in the last day lecture, in the very beginning, we have discussed about its spectra or the band. The band belonging to the S37 is shifted by the smaller wave amount, that is the longer wavelength side of that is the red, red wavelength side. If you remember, in a last day class, we have mentioned it, this one. So this SCL31 is the lower side of this my wave number, and this 35 is the higher side of that wave numbers. Okay, so now corresponding to the SCL35, and the shift increases with the order of the band. Once it is shifted, once you are taking that the orders of the band, then the shift will be increasing. So in fact, every line of each vibration band, rotation vibration band, has a weaker comparison of the longer wavelength side to this vibrational shift of the each line is added a rotational isotopic effect also. So now once we are looking at in this band, so then these bands are also influenced by the isotope effect by the rotational spectra as well. For a molecule like S35 and the HCl35 and the DCl37, rho is nearly 0.7, quite different from one, and the shift is so great that the bands lie in a quite different spectral regions. Because what we assume that in that case, this rho is approximately equal to 1. However, this is only the 70%, only the 0.7. In that case, once we are looking these bands and they are appearing in a spectral line in a different places. You may have a very different bands in a spectral line. This is all about this isotope effect and how to estimate the force constant in the case of the rotational spectra. Now, in the next class, I'll be discussing about the molecule as a vibrating rotator. Now, we'll be considering that this rotation and the vibration all together as to study that the fine structure of the infrared bands. So what we were discussing, that if you remember in the yesterday class itself, I said that within a band you have a fine line of the fine line structure. These lines are representing your rotational spectra. Then we'll be discussing, and this is very very crucial lecture for tomorrow. It would be a bit lengthy itself because we'll be discussing that the molecule as a vibrating rotator, where we'll be discussing that the infrared bands of this R branch and the concept of the R branch and the P branch, and this is very important. We'll be discussing tomorrow itself. Thank you.